Okay, hi. This example is on using the normal distribution to calculate probabilities and percentiles for normally distributed variables. The normally distributed variable we're going to be using in this example is duration of a human pregnancy. There is a large sample Norwegian study done that estimated a mean duration of 281 days and a standard deviation of 13 days. The study, if you want to read about it, there's a reference down there. The Scandinavians tend to collect lots and lots of data on their citizens, and so they have quite a few very large sample studies. This is one of them. We're going to be using this app right there. And so let's get going. First off, I want to identify a couple things here. So mean duration is 281 days. I'm going to call that mu equals 281. It's a sample mean, really. It came from a study. We hardly ever actually know what the population values are for the variables we're working with. So in this case, I'm going to assume that the mean is 281. And I'm going to assume that the standard deviation, which we denote as sigma, is 13. Okay, first question. How many standard deviations from the mean is a pregnancy lasting 300 days? And what proportion of human pregnancies last longer than 300 days? So this first part, how many standard deviations from the mean? When you hear that language, we're talking about a z-score. We're talking about standardizing the value of a variable and converting its units from whatever its original units were to number of standard deviations away from the mean. And so here's our formula: z equals x minus mu over sigma. And so I'll plug in the values. X is the value that we want to standardize. In this case, it's 300 days minus the mean of 281 over the standard deviation of 13. And you should get 1.46. So 1.46 is a number of standard deviations. So 300 days is 1.46 standard deviations above the mean. Okay, the second part says what proportion of human pregnancies last longer than 300 days. This is equivalent to saying what is the probability that a human pregnancy will last longer than 300 days. So what we want, if I want to write it formally, is we want probability that x is greater than 300. And we know that that's equivalent to the probability that z is greater than 1.46, because we just converted 300 to 1.46. Now, the only reason we can do this is because we're assuming that pregnancy length is normally distributed. If I am willing to make that assumption, then I can use this normal probability app and figure out what's the probability that z is greater than 1.46. I'll go ahead and draw the picture first. It's always nice to be able to draw a picture of these things before you go doing your calculations. So that's not very good. So there's my normal distribution, and what we had, okay, I'm going to write it as x first. So x is pregnancy length. It has a mean of 281, and we took 300 and we converted it. So 300 is 1.46. That's out here somewhere. Whoops. That should be 300. And so what we did when we converted to z is we just said, okay, let me rewrite this axis as z, which always has a mean of 0, and 300 was converted to 1.46. and this is the area that we want. That area is probability that z is greater than 1.46, and that's what we want to find, so we'll pull up the app. Select the right-hand area and make that z value 1.46, and there's our answer, 0.0721. Okay, so that's the answer to the proportion question, and that's the answer to the number of standard deviations question. Okay, next one. What is the probability that a pregnancy lasts fewer than 290 days? So again, I'm going to use the z formula, z equals x minus mu over sigma. Now I'm going to convert 290 to z. That turns out to be 0.69. And I'll draw the picture again over here. X 281 and 290. I drew that a little bit too far out. Let me move it in a little closer. Something like that. 290 and then z mean of 0, and we found that that is 0.69. Now I want to be clear that that 0.69 is a number of standard deviations above the mean. I drew that on this horizontal axis here. When we do these probability questions, all of our probabilities and our proportions are numbers between 0 and 1, and sometimes it gets easy to confuse. If you've got a z value that's between 0 and 1 and a proportion or a probability between 0 and 1, it's easy to get them confused. So I want to be clear, 0.69 is not a probability. It's not a proportion. It's the number of standard deviations above the mean that 290 lies. So I'll draw the picture of what we want here. We want the probability that pregnancy lasts fewer than 290 days. So fewer means I'm going to shade to the left here. That's the area that I want. And so that area is probability that x is less than 290, which is also equal to the probability that z is less than 0.69, and we'll just make the app look like that. So I want area to the left. Z equals 0.69, and I get 0.7549. Oh, whoops. Okay, one thing I want to note here, as soon as I drew this picture and I shaded that area, before I even calculated the probability, I knew it was going to have to be bigger than 0.5. And that's because this picture I drew, we can see clearly this takes up more than half of the distribution. Half of the distribution would be on either side of the mean. So if I have a value above the mean and I'm shading to the left of it, then that area must be greater than 0.5. That's one reason I always recommend drawing the picture before you do these problems. It can give you a sense of what sort of number to expect. It also makes it a lot easier to figure out what to put in here, because you just make the applet look like the picture you drew. Okay, next one. What is the 20th percentile value for pregnancy duration? What is the 80th percentile value? So percentiles refer to values of a variable such that the given percentage falls below. So I'll draw the pictures first. So for 20th percentile, we're going to want a value such that there's 20% to the left, or 0.2 will be the area under this curve to the left of the value we draw. So that looks like it's somewhere around there, maybe. And so what we're saying here is area equals 0.8, and then area equals 0.2. And I want to know what's that value right there. And for the 80th, it's just going to look like a mirror image. So that's a really lousy normal distribution. Let me redraw that. It's a little harder to draw these normal distributions on a screen than it is on a whiteboard. Okay, 80th is going to be somewhere around there, where area down there is 0.8, area there is 0.2. So I'm just going to make my app look like the picture I drew. Let's see, I want area. Okay, so I don't want to enter a z-score. I was entering z-scores before. Now I want to enter an area. I can say area of 0.8, or I could say area of 0.2, and you'll notice that my lines didn't change. Here we go. I've got z equals negative 0.842 down here and positive 0.842 up there. I'm going to change this back to 0.8. So what's going on here is that this z distribution, it's symmetrical around 0. So if I have 20% down here, it changed it to 0.1999. If I have 20% down here to the left of negative 0.842, that also implies I'm going to have 20% to the right of positive 0.842. So z equals negative 0.842, and over here we have z equals positive 0.842, and now I got to convert that to a pregnancy length. That's a z-score. That's a number of standard deviations away from the mean. I want that to be a value in terms of my variable. So the formula is x equals the mean plus your z value times the standard deviation. So mean is 281. My z value is, well, I'm going to put minus because it's negative 0.842 times 13, and that is roughly 270. I'm rounding this a little bit. And then over here, same deal. This time it's plus 0.842 times 13, and that's roughly 292. And there we go. Those are our answers. Okay. What is the duration of a pregnancy that is 3 standard deviations below the mean? So you can probably sort of work this out even without writing down a formula. 3 standard deviations below the mean, so take the standard deviation, multiply it by 3, subtract it from the mean. But let's do that formally. It's the same formula as before. Basically, 3 standard deviations below the mean, that's a z-score. That's z equals negative 3. Z equals negative 3, and I want to convert that to x. So we'll use x equals, again, mu plus z sigma 281 minus 3 times 13. And that's 242. I'll draw my 4 a little better. Or not. Okay, 242, and I'll just draw that on our picture as well. In this case, we don't need the app for this one. We don't need to assume a normal distribution to do this. We could have done this for a non-normal variable, but let's just go ahead and draw on the picture of our normal distribution. What we did is we took z, which has a mean of 0, and we said way down here, roughly, is z equals negative 3, 3 standard deviations below the mean, and we just converted that to x. Okay, on x, my mean is 281, and that is 242. Okay, 5. What value separates the top 2% from the bottom 98% of pregnancy lengths? I'll draw it first. Top 2 from bottom 98, so that's going to be somewhere up here. And area equals 0.98 below, and then area equals 0.02 above. Another way of saying this is, what is the 98th percentile for pregnancy length? We'll get it in terms of z first, so I'm going to want an area to the left, so let me click on left and then make that area be 0.98, and we get z equals 2.054. I could have used the right tail as well, so let me mess these up a bit. Click on the right tail and say the right tail should have 0.02 in it. Whoops. 0.02. And I get the same thing, 2.054. So that is z equals 2.054, and so x equals the mean plus z times the standard deviation, and that comes out to about 307.7. Okay, last one. What two values enclose the middle 95% of pregnancy lengths? We already saw a middle 95% question in the notes. Turns out that middle 95% is a concept we're going to be coming back to in this class. In Module 5, we're going to talk about confidence intervals, and there's the most popular kind of confidence interval is called a 95% confidence interval, and then the method we're doing right here is going to be the foundation for how we make these confidence intervals later on. So what I'm going to do is draw my distribution. Where I have 0.95 in the middle. Now if I have 0.95 in the middle, that implies I have 5% left over split between the two tails, which means I've got 2.5% in either tail. Okay. And we'll get our z values. They're the same ones we got in class before. So I'm click on my middle area. Oh, I'm almost there. That's 0.96. 0.95. Z is plus or minus 1.96. And if I unclick on this and click in that tail, I've got 0.025, 2.5%. And up here I've got 0.025, 2.5%, 95% in the middle. And so Z equals negative 1.96. Z equals positive 1.96. And I just got to convert those into x, so that is 281 minus 1.96 times 13. This is 281 plus 1.96 times 13, and we have about 255.5 to about 306.5. That's it for the math. The one last thing I want to say is I want to remind you of what I reminded you in class about, which is that these numbers should really be treated as approximations. So if I wanted to interpret this I could say, hey, according to our calculations, 95% of all human pregnancy lengths fall between 255.5 days and 306.5 days. The half-day thing, maybe we should be rounding that. More generally, these decimal places, 307.7 or 0.7549, that's awfully precise. And that level of precision comes from making some assumptions, such as pregnancy lengths are normally distributed, the population mean is 281 days, the population standard deviation is 13 days. All of these are approximately correct, but they're not exactly correct. I don't know what the population mean is. Of course, the population mean will be different for different subgroups. Maybe it will be different in different countries, different for different time periods. This was done in 1990. Maybe it's changed since then. So I'm saying population mean is 281. It's approximately 281 according to the best information I could find. The distribution is normal. Not much out there is perfectly normally distributed. So the distribution is approximately normal. So the inputs for all these methods are approximate, which means the outputs are approximate as well. And so 0.7549, I might believe the 7 and the 5. I'm not going to take the 4 and the 9 all that seriously. Likewise with 307.7, it's probably better to just report that as 308. And even then, maybe the 308, maybe it's really 309, 310, 311. I'm not quite sure. 308, roughly, is about the best we can do with the information we have. Okay, that's it for this example. I hope this has been helpful.